All right, we've reached it. We're at the home stretch. We're in the last topic of the course. The last topic of the course involves taking a look at molecules and considering their real life shapes. We really don't think about that. And I find this is certainly true with me, and I find this to be true with most students, that when we think about molecules and atoms up to this point, we either have absolutely no conception of that visually from a realistic point of view, like considering them to be real structures, or we just have some very basic things that we've done, like modeling that we've done in this course, which is essentially visualize things as little balls. And while the visualization of things as little balls isn't bad, it's just not, perfectly precise. And even the thing that we're going to do today isn't going to be perfectly precise, but it'll add a layer of precision that we haven't gotten to yet. And so when we think about molecules, which are, more than one atom connected together, we've just kind of drawn dots just sort of stuck together with each other. And we haven't really, maybe we draw two dots with a line in between, but that's about as complex as we got. And so what we want to do is we want to think about, well, what are the actual shapes of molecules? If a molecule is 3 or 4 atoms, 5 atoms, what shape is it in real life? And the shape that it's in real life is dictated based on physical properties. And we're going to talk about that a little bit more in detail in just a second. Now, in general chemistry, you're going to talk about the shapes of molecules that have 2 atoms, 3 atoms, 4 atoms, 5 atoms, 6 atoms, and even 7 atoms. In organic chemistry, you won't talk about the specific shape of molecules but you will talk about the general shape of a molecule that may have lots and lots of atoms. And so what we're going to learn is that there are names and there are actual geometric structures associated with these shapes. And they're not random, right? They're not random. They actually have particular shapes that are predictable. In this textbook, it is chapter 10. Mm-hmm. Okay, and so here's the deal. At the very basic level, it's all about electrons. We spent the last bit of learning talking about quantum mechanics. We did a little bit of stuff with energy and light, but then we quickly transitioned into a discussion about electrons and quantum mechanics and how do we think about electrons and their energy levels and electron configurations and what do electrons do as far as populating orbitals and delivering electron configurations, and how do those work, make atoms bigger or smaller based on the number of electrons they have. And we talked about some periodic trends. At the end of the day, I kind of remember at some point in my undergraduate chemistry career, and I think in the junior level course, it just kind of hit me. And I just looked at the professor and I just said, chemistry is just about electrons, isn't it? And he looked at me and he said, you bet your sweet bippy it is. And at the end of the day, atoms and molecules definitely have protons and electrons, or excuse me, protons and neutrons. But chemistry is about electrons. The things that we study, they all have to do with electrons. Now, it is electrons that are in the vicinity of protons and neutrons, and the protons have an effect on what the electrons are doing. But at the end of the day, it's the electrons that are really doing everything and forcing us to think about things in certain ways. So with that being said, the same thing really does apply with geometry, with the shape of molecules. I said that there's a predictable pattern, right? That you can predict what a molecule looks like based on its conditions. And that pattern is going to be based on one simple principle. And it's something you guys already know. And that's that electrons don't want to be next to each other, right? They are negatively charged particles. I know I'm personifying them and I'm saying want, but they're negatively charged particles, and the Coulombic interaction of two negatively charged particles is that there's a repulsive force. Now, if we're talking about molecules, the electrons in the molecule have to be, and remember from a quantum mechanical perspective, B is somewhat uncertain, that they have to be, the electrons have to be in the molecule, right? So I can't just say, well, if the electrons don't want to be next to each other, we'll ship one off to Australia and the other one off to Alaska, and that's pretty far away. And then no, they still have to be in the molecule. And so that's what's going to dictate the shapes. And so if you think about that, how far that electrons want to be apart from each other as far as possible within a molecule, then you'll start to see that that really is all, that's really all about what the shape, that's where the shapes come from. Now, there's going to be two different methods that you can use to think about the shapes. And this is what I mean by this. I am going to expect that if I give you a formula, you'll be able to draw a picture, or at least you'll be able to draw a picture that's good enough that you'll be able to tell me what the actual three-dimensional shape of the molecule is and use its correct name. There will be names associated with these shapes. Now, for some people, thinking in 3 dimensions is a breeze. And it honestly doesn't have anything to do with their ability to do chemistry problems. My favorite story is about a guy who took organic chemistry with me. And, and he wasn't the best student. I'm going to be honest with you. He was a C student, a low C student. But then at some point in the class, we started to talk about 3-dimensional shapes. And we talked about it in a really deep level. And briefly, I'll say that molecules can be left-handed or right-handed. And that's all I'll say about that. And it takes some practice to visualize a molecule in 3 dimensions to decide whether it's the left-hand or right-hand version of it. Now, the guy wasn't great when it came to acids and bases and physical properties and formulas and hybridization and all this other business. But the guy was a savant when it came to seeing things in 3 dimensions. I would get a problem written on the board, and before I finished turning around, he'd be shouting out, left hand, right-handed. He already knew. It's because the visualization in 3 dimensions is completely disconnected from your ability to do problem solving. They're 2 different skill sets in the mind. And so some of you guys that are A students might struggle a little bit with seeing things in 3 dimensions. And some of you guys that are C students might say, oh, this is really easy. I don't know why everybody is having a problem with it. So this goes back to my 2 different ways to approach this bit of learning. One way is to just think about the molecule in 3 dimensions and say, oh, well, that shape is a pyramid, and that pyramid has 3 sides. So since it's the shape of a pyramid with 3 sides, that's the trigonal pyramidal shape. Or, oh, that's a tetrahedral. That's a tetrahedron. So the shape is tetrahedral. Some people aren't going to be able to do that. And so the other option is to just, you have to memorize. You have to memorize the shapes and their names. And you're going to have to I'll show you a way to use the information about electrons to draw a simple picture. And even though that picture won't be a 3-dimensional picture, you'll be able to use that picture to then decide what the shape is. And so I want to make sure to remind folks that when you draw pictures, unless you specifically include 3-dimensional information by being artistic and drawing something that's close and something that's far away in an artistic way, you're not really including 3-dimensional information. That 3-dimensional information is implied somewhere in that picture, and can be sorted out based on those implications, but it's not necessarily included from the first drawing. Now you can draw it that way, but you know, we're not, and I'll show some different ways to draw that. And I'm going to use some models in a second to connect them together. But again, you don't have to have that three-dimensional visualization skill. You can just sort of memorize what's going on with these electrons. Okay, and so I don't want to get too. I want to make sure to keep this slow because I can do this pretty quick, and I don't want to get bogged down in that too fast. But let me go ahead and show you the three basic shapes that you're going to have to know. Now, there's three basic shapes. Those three basic shapes will have shapes that stem from those basic shapes. And I'll show you what I mean by that in just a second. So there's only going to be three parent, and I'm going to start to call them parent shapes, but then there'll be a set of sub shapes under each of those parents. And so let's start off with the simplest version, right? So if you go back to geometry and you go back to your geometry course, what is the only possible geometry between 2 points? If you think about that, what is the only possible geometry between 2 points? Yeah, exactly, a line. So if you think about atoms as being points, 2 red balls representing atoms, the only possible geometry that this takes is a line, right? So what do you guys want to call the shape of a molecule when it's a line? Yeah, we're not real clever here, folks. Chemists are lazy. Yeah, linear. You got it. So this is a linear shape, right? And I can point it towards the camera, and you can see that the front atom eclipses the back atom because it's directly in a line. Well, what about if you have, this is 2 atoms, right? What about 3 atoms? What about 3 atoms? This is what I do. I say, okay, well, imagine that your head is 1 atom. And that so this is what happens, right? Folks think 3 points, angle. So it's a triangle, right? So remember that a triangle, that a plane, and a triangle is a planar shape, does require at minimum 3 points. But that doesn't, all we're saying about this is that now that there is the possibility to be an angle, what is that angle going to be? So if you think about it, you have 3 atoms. Imagine that your head is 1 of those atoms, and you put your arm out. You see it's kind of connected to your head. Imagine that your head is really big, right? So your arm is connected to, then you got another arm, right? And so they're both connected together. Here's the angle, right? H-E-double-L. I love chemistry. No? Yeah, right. Somebody said acute angle. If your arms are bonds, what are bonds made out of? Think about that. You're forgetting what bonds are made out of? What is a chemical? Yeah, bonds are electrons, right? And electrons what? They love each other, don't they? They want to be right next to each other. No, they don't want to be next to each other. They want to be as far apart from each other as possible. So what shape does it take? What's the angle that your arms can make if they're as far apart from each other as possible? No, that's not any angle, right? So here's a 90-degree angle. Are they as far apart from each other as possible? Now they're as far apart from each other as possible. So when you got 3 atoms, What shape is it? Yeah, it's still linear. It can make an angle. You need 3 points to make an angle, but what is the value of the angle? Think about that. What is the value of this angle? Measure it in degrees. Yeah, it's 180 degrees. That's what it is. So it's still linear. I mean, this is just a model, right? It's just a model. It's not about the type of bond. The question is asked, is that some sort of bond? Now, we're going to talk about single bonds, double bonds, and triple bonds in a second. We're talking only about covalent bonds, right? Because ionic bonds don't work like that. Ionic bonds aren't sharing electrons. Ionic bonds are just negative particle, positive particle stick together. Boop. That's all that is. And we're not talking about sharing electrons, right? That's not okay. Ionic bonds don't share electrons. They're just negative and positive. Covalent bonds share electrons, and this is what we're talking about today. Covalent bonds. The angle is 180 degrees. It could be other angles. Let me ruin my molecule. Look, you see me bending it? I can't bend it too far, but that's less than 180. Bend it back. Now it's 180 again. What about 4 atoms? What about 4? Now, usually in a lecture, I'd get up and I'd hop around on one leg. Square. I'd hop around on one leg. And I'd say, well, let's imagine our legs are bonds too. So maybe you can get up right now in your bedroom and you can hop around on your legs. Use your legs as a bond. Use your arms as the other bond. You need to keep all the bonds as far apart from each other as possible. Well, we're adding more atoms, right? So we talked about 2 atoms. The only possible geometry between 2 atoms is a line. That's just basic geometry. Then we said, okay, let's get 3 atoms. Now, we're assuming, in all of this assumption, we're assuming that 1 atom in the middle, right? 1 atom in the middle. Okay, well then, how about how far can the other atoms be apart from each other? If 1 atom is in the middle, how far apart can they be? Because they got to be connected, right? If I just take them apart, then I can throw one in the other room, this one over here, and throw that one behind me. No, they got to stay in together into a molecule. Right? But what if I add another atom? Is that as far apart from it as it can be? Is that as far apart as they can be? Well, they can be further apart than that. What are these angles? What are the angles I'm showing you right now? These are 90, right? Could the angles be greater than 90? Oh, if imagine a circle, right? What would be all of the angles? If you can imagine a circle, what would be the sum of all the angles? 360, that's right, 360. Okay, so 90 plus 90, what is that? 180. What's this angle? This angle's also 180, so 180 plus 180, yep, that gets you 360. Can you make all the angles, so can you make the 90 degrees angles bigger and still get up to 360? How do you do that? Yeah, 360 divided by 3. Yeah. 360 divided by 3. What are the angles here? What's this angle? Yeah, 360 divided by 3. It's 120. Is 120 bigger than 90? That's right, boys and girls. 120 is a bigger number than 90. So these bonds are further apart. Now, these bonds are closer than 180, but the other two bonds are closer than 90. And so as far apart as it can be is 120 degrees apart for every bond. So this one is linear, right? This one is linear. This one is linear. Do you call this one linear? Is this one linear? It's kind of a triangle shape. That's right. What else is it, though? What other geometric property does it have? It is a triangle shape. Yeah. What else? Is it linear? Yes or no? In order to have volume, you need a three-dimensional shape. Is this three-dimensional? I mean, it's three-dimensional because they're balls that I'm holding in my hand, and they're three-dimensional in my hand. But the overall shape, does it have 3 dimensions? It's got length. It's got width. But does it have a height? No. This isn't 3 dimensions. Is this one? How many dimensions is this one? It's got a length. Does it have a height or a width? Yeah, this is 1 dimension. Oh, 1 dimension. It's line. It's a line. It's linear. That's 1 dimensional. This one was, how many dimensions did it have? 1 length and width, but no height. Okay, so what do we call 2-dimensional geometric objects? 2-dimensional geometric objects. There's a word for it. I'll give you guys a clue. It starts with the letter P. Not polygon. It's also the thing you ride on in the air. Yeah, it's a plane. So someone said this was a triangular shape. But it's also planar. It's more dimensions than a line, and so that means that it's a plane. So here's this triangular shape, but it's a plane, and that's exactly what this shape is called. It's called trigonal planar. Trigonal meaning triangular, trigonal planar. That's what this shape is. Okay. What shape could it, this was 4 atoms. What happens if there's 5 atoms? We went from 180 degrees to 120 degrees. What now? Which shape will it be now? 5 atoms. Still 1 atom in the middle. Pyramid like this? 90 degrees square. That's definitely like a common answer, right? Square. Let me get that going on here real quick. Is this as far apart as 4 bonds can be? Yes or no? No. No. 4 bonds can be further apart than this. We'll get to the name in a second. Is this shape 3-dimensional or 2-dimensional? This shape. Yeah, this is still 2-dimensional. This is still a plane. If you allow the molecule to be 3-dimensional, yeah, then the angles can be greater than 90 degrees. Does anybody know what this shape is called? So it's a little bit harder to see, but there's a that. This one's in the middle. The black one is in the middle. Yeah, it's called a tetrahedron. This is a 4-sided polygon of equal sides, a tetrahedral, or a tetrahedron. It's in the tetrahedral shape. So students we go from here to here because students often miss the idea that the molecule doesn't have to be planar. It could be 3-dimensional. It could have a volume. Okay. And so those are the major shapes. What are they again? So let's review. What are they? What are they? I gotta rebuild. Linear. Trigonal planar. And tetrahedral. The question is asked, what does hedral mean? And I actually don't know the answer to that. I'm sure there is a definition, but I don't actually know. So again, the 3 major shapes, the 3 parent geometries: linear, trigonal planar, and tetrahedral. We're going to just limit it to video today, and we're going to do some writing on Wednesday. Okay, those are the basic shapes, but as I said, there's going to be subshapes, and the reason is this. And I'm just introducing it all, and I'm going to go back and I'm going to write it all down and with the whiteboard in a second. Well, we'll do it on Wednesday, but I'm just trying to get this instilled in the best visual way possible, with the limits of the technology that we have. So, I mean, the best I can do right now is take my models and put them up on the board in front of the camera. So we've seen the 3 basic shapes: linear, trigonal planar, and tetrahedral. And I said those are going to be the basic shapes, but there'll be subshapes underneath each of those. And the reason is this. There's 2 different types of geometries that we consider. One geometry is called the parent geometry, or the other word for it is the electronic geometry, the electron geometry. So what that does is that says, okay, I want to consider the shape of the molecule considering all of the electrons. What does that mean? Well, in a minute, what we're going to see is that sometimes the electrons don't participate in bonds. Sometimes the electrons around an atom do not participate in bonds. We call those lone pairs. They're by themselves. They're pairs of electrons by themselves. They're not in bonds, but they're around the atom, the central atom of the molecule. And so they'd still contribute to the geometry. So when we say electron geometry, we're considering the geometry of the molecule, including the influences of all of the electrons, even lone pairs, even if they're not bonded to different atoms. And so what I want to do is I want to take this and I want to say, well, let's pretend that there's a lone pair. And the lone pair is still attached to so this is no longer an atom. Let's be specific. This now represents a lone pair of electrons. The lone pair of electrons is still on the atom. So it still influences the geometry. And so for simplicity's sake, ooh, you know, look what I have. I have something in the model that represents a lone pair. Look at that. There it is. Electrons don't want to be next to each other. So even if this pair of electrons is not bonding another atom, it still influences the geometry in the same way. You still have 1, 2, 3 groups of electrons, and so those groups of electrons influence the geometry. So what's the basic shape here? I took one atom off and I made it a lone pair. What's the basic shape? What's the parent shape? Has it changed? It's still trigonal planar, right? It's still trigonal planar. Here, I did it with this one. What's the basic shape here? It has the same influence on the geometry. Still tetrahedral. It's just that instead of having an atom, it's a lone pair. Instead of being a bond to an atom, it's now just a pair of electrons hanging out by itself. So there's 2 different types of geometry that we want to consider. The first geometry I just talked about, that's the parent, or the other word that I use to describe it is the electron geometry. You might even hear electronic geometry, but I'm going to stick with parent geometry will be the word I use most often, but I will use electron geometry pretty frequently as well. The other word that we use, the other type of geometry that we want to consider is the molecular geometry. And the word molecular geometry just means the shape of the molecule considering only atoms. Considering only atoms. So we ignore lone pairs, if there are any. And we talk about the shape with only atoms. So what's the parent geometry here? Linear, right? Linear. Let's get rid of one of the atoms and let's make it a lone pair. What's the parent geometry here? Still linear. Okay, let's consider the shape the molecular geometry, let's consider the molecular geometry the shape of only the atoms. So what I'm going to do is I'm going to get rid of the lone pair. It's still there, but I don't want to think about it. What shape is left? It's still linear, right? It's still linear. So when it comes to a linear molecule, there really aren't any subshapes, because even if there is a lone pair, then you still get just a linear geometry, right? If one of those bonds in a 3-atom molecule becomes a lone pair, you still just got 2 atoms, and the only shape between 2 atoms is still just a line. Done. Checked off linear structures. We've got all of the different possible structures. For the linear electron geometry, for the linear parent geometry. Okay, let's go back to trigonal planar. All right, so here's that trigonal planar parent geometry. 3-sided planar geometry. So the parent geometry is trigonal planar. Now let's replace one of those things with a lone pair. What's the parent geometry here? What's the electron geometry? That's right. Some of you guys are a little uncertain, but some people are certain. It's still trigonal planar. But now let's examine the molecular geometry. The molecular geometry, remember, is the geometry that only the atoms take. Well, here's a lone pair. It's not an atom. So let's get rid of it. Remember, chemists are lazy. We don't come up with really clever names. Yeah, that's not trigonal planar anymore. What is this? V for vendetta, huh? Obtuse angle. It is an obtuse angle, but it's getting closer. Replace the D. There it is. It's just bent. That's all it is, bent. So again, trigonal planar parent geometry with 4 atoms. It is an amazing name. But what if one of those atoms was a lone pair? The parent geometry is still trigonal planar. But the molecular geometry is no longer trigonal planar. The shape of only the atoms is bent. So if you have all atoms, the electron geometry is trigonal planar, and the molecular geometry is trigonal planar. But if one of those atoms is a lone pair, the electron geometry trigonal planar, but the molecular geometry is different. It's bent. Okay, well, what if there are 2 lone pairs? What if there are 2 lone pairs? You still only have 3 groups of electrons. And I keep calling them groups of electrons because when we draw pictures, that's how we're going to figure it out. We're not going to have molecules. We're going to have pictures. And in the pictures, we're going to have to count the groups of electrons. We still have 3 groups of electrons here. What's the parent geometry? Yeah, it's still trigonal planar. But the molecular geometry is different, right? If I take away the lone pairs and examine the shape that only the atoms make, what is that? Linear. Linear. So for the trigonal planar geometry, there are three possible there are three possible molecular geometries. It could still be trigonal planar, but it could also be bent. And if there's a rare situation where there's two lone pairs, it could also be linear for the molecular geometry. Okay, let's do tetrahedral. Tetrahedron. There's 4 atoms around the central atom. So in this case, there's 4 electron groups. There's 4 electron geometry groups. All 4 of these groups happen to be bonds to other atoms. But they don't have to be bonds to other atoms. Could be a lone pair. Could be a lone pair. There's still 4 groups of electrons. So what's the parent geometry here? What's the electron geometry? It's still tetrahedral. But now the molecular geometry is different. And so remember, the molecular geometry considers the shape of only the atoms. This one is a little harder to see, so I'm going to try to... You know, this... Yeah. It's a 3-sided, very shallow pyramid. So yeah, it's not double bent. No, it's just it's a 3-sided shallow pyramid, and so it's called trigonal pyramidal. It's called trigonal pyramidal. It's a 3-sided shallow pyramid. So look, here's one side, here's the other side, and here's a side too. I need to switch my hands. So there's 3 sides to the pyramid, and it's this atom is slightly higher than these atoms, and so it is actually pyramidal. So this is called trigonal pyramidal. This one is the hard one, right? The hard one to remember is trigonal pyramidal. So the parent geometry, it's still tetrahedral. The molecular geometry is called trigonal pyramidal. Okay, so what if there were 2 lone pairs? There's 2 lone pairs. I'm gonna write it down on Wednesday, so don't worry. It's trigonal, O-N-A-L, no E. Trigonal pyramidal. Yep. What's the parent geometry here? Yep, still tetrahedral, right? Still 1, 2, 3, 4 geometry groups, 4 electron groups. So it's still pyramidal, or excuse me, back up. It's still tetrahedral as it's electron geometry, it's parent geometry. But let's consider the shape that only the atoms make. Yeah, we're not, chemists are lazy, right? We're not going to come up with some new name for the same shape. It's bent. It's bent again. It's bent again. Okay. I don't even know of an example like this. I don't even know of an example like this. But let's just think about it hypothetically. What if there were 3 lone pairs? What if there were 3 lone pairs? How many geometry groups are there? 1, 2, 3, 4. So it's still tetrahedral. But what would the molecular geometry be? Right, exactly. You're starting to get on top of it. Linear. Okay, so what I'm going to do is I'm going to leave it there for 2 reasons. One, what we did is we focused entirely on looking at models. And so I think it's good to have the video, just leave it there. This completely focused on models. The other reason is my iPad's about to be dead, and so I'd spend 2 minutes writing on the iPad, and then it would be dead anyway. So let's not even go down that road. Let's look forward to what we're doing on Wednesday, the next time we meet. Linear is always linear, whether it's the parent geometry or the molecular geometry, because there's no other geometric shapes underneath that. It's at that point, you're always talking about 2 points, and the geometry between 2 points is a line. Tetrahedral can be a variety of different shapes, right? And it's the one that has the most different shapes. Now, what you guys should be thankful for is that in Chem 107, we don't make you think about the shape of a molecule that has 6 bonds and what are the different shapes now? And so on and so forth. So in general chemistry, we'll get a little bit more in depth into that, but in introductory chemistry, we're going to leave it there at tetrahedral. So you do have some shapes to think about. It's called octahedral. That one was called octahedral. There are some, so you do have some shapes to think about. You have to think about the 3 parent shapes: linear, trigonal, planar, and tetrahedral. And you have to think about the subshapes. And really, you don't have to worry about linear because it's still going to be linear. Tetrahedral, there's only one shape that you really need to know, and that's bent. In tetrahedral, there's 2 shapes, and the hard shape is trigonal pyramidal. And so what we'll do next time is we'll take those ideas, and then we'll learn the notation. We'll learn on how to take a formula like CH4, and we'll learn how to actually count the number of valence electrons that are in the molecule and use those valence electrons to draw a picture. And with the valence electrons in the picture that we'll draw, we'll end up with a certain number of electron groups. And we've already kind of got this idea that counting electron groups is what gets us to the geometry. And that's what we're going to do. We're going to count electron groups. And so we'll practice that on paper next time. And so I'll leave it there for now. See you guys later.